Visual analytics provides intermediate results in the middle of computation to address a long computational delay. However, such intermediate results are uncertain, so findings from these results can turn out to be incorrect for the entire data. In progressive visual analytics with safeguards, we suggest to risk the uncertainty, but we allow humans to leave safeguards every time they risk the uncertainty.
Magazine-style narrative visualizations can be challenging due to the need to go back and forth from the text to the visualization. We use eye tracking to monitor which sentence is currently being read and trigger visual links between that sentence and the corresponding data points in the visualization. Results show that the gaze-driven links increase comprehension of the documents without hindering reading time.
In this presentation, we introduce a provenance library, Track, which makes implementing provenance in web-based tools easy. Track introduces a novel storage model for web-based provenance tracking and has an associated history visualization, which can be fully customized. Track also contains multiple ways to save and share individual states or entire sessions of an application and ensures that exported data is easy to analyze in interesting and unique ways.
Do these three essays construct their argumentation similarly? Where in this table of argumentation data from the previously seen texts can I find certain argumentation patterns? Do these three argument maps depict the same argument? We have developed a visual analysis system for argumentation in essays that can answer these questions at a glance. You want to know how it works? Come to my talk.
Predictions made by machine learning models can be hard to understand. Counterfactual explanations explain model predictions by telling the users how to obtain the desired prediction with minimal changes to the input. We introduce DIS, an interactive visualization system that supports counterfactual-based explorations on individual instances and data subgroups. Please check our paper for more details.
Out-of-distribution samples refer to the test samples not well covered by the training data, like these black cats. They are misclassified with high confidence due to their black bodies. To explain why these samples are out of distribution, we developed OOD Analyzer, a visual analytics tool which provides an ensemble detection method and a grid-based visualization to detect and analyze out-of-distribution samples.
Asteroids have always been and will always be a threat to life on Earth. Most likely, an asteroid will hit deep water, but what properties will actually lead to a threat like a tsunami? Ensemble simulations are a common tool to understand the effect of different parameters like the size of the asteroid. We propose an interactive visual approach to help analyzing deepwater asteroid impact simulation ensembles.
In this paper, we investigate design choices for work correlate maps by domain experts. We tackle two research questions: how do domain tasks influence the design choices, and what equal error projection is preferred. Through a survey, we collected 40 correlate maps designed by 20 social scientists, and our analysis suggests that the choices vary across tasks, the projection was most important, and the equal error projection was preferred.
We demonstrate that people can use the spatial cues available in virtual reality to help them effectively remember and recall scholarly articles. We used a virtual coffee shop and asked participants to remember 4 abstracts from scientific publications, and we termed this method a virtual reality memory palace variant.
Tableau helps you see the stories in your data. It's designed to help you be smarter, so you can make better decisions faster. With Tableau, you can keep on asking questions in the data until you discover the root cause. Share your analysis securely. Your entire organization can access these interactive dashboards from any browser or mobile device to find their own answers. Tableau. Answer questions at the speed of thought.
In our current work, we visually compare two cohorts of segmented and classified tissue images, originated from single-cell omics data. To that end, we developed data-driven and interactive workflow implemented in a multi-linked view system. Finally, we show the effectiveness of our workflow through specific case studies.
As commonly known, dimensionality reduction techniques and their interpretations are complex, biased, and uncertain. In drug design, this highly complicates the search for similar and new chemical compounds. To overcome this issue, Canva brings comparison of different molecular descriptors and properties into one tool, featuring planar, 3D, and table views for evaluating the trustworthiness of high-dimensional data projection.
general audience is likely to become distracted during the ever-changing animated visualization and reluctant to consume the entire animation. Informed by the role of foreshadowing that builds the expectation in film and literature, we formulate and apply visual foreshadowing on animated bar chart to improve its engagement. In addition, we implement a proof of concept authoring tool and conduct a user study to learn the efficacy of engagement enhancement of our approach.
Deep neural networks are vulnerable to maliciously generated adversarial examples. This brings high risk in applying these networks to safety-critical applications. We develop a visual analytics approach to explain the root cause of such wrong predictions. Our contribution contains a constrained datapath extraction method, a river-based visualization, and a contribution analysis method.
We present our work, Visual Analytics-Based Decision-Making Environment for COVID-19 Modeling and Visualization. In pandemic situations like COVID-19, public health officials have to prepare and evaluate response plans. They need tools to explore and compare model simulation outputs, study different spread scenarios, and analyze the impact of mitigative decision measures. If you want to know more details about how we support this, please attend our talk.
The ever-evolving landscape of malware detection and evasion creates a constant catch-up contest between the defenders and the adversaries. We created a system which submits and analyzes a malware sample with Cuckoo Sandbox and then animates the battle between the malware and the anti-malware system. The Gotta Evade 'em All system is a useful tool that uses a familiar concept based on Pokemon, allowing the understanding of malware evasive behavior to be more accessible.
Scatterplots and parallel coordinates are widely used for visualizing multivariate discrete data. However, for multivariate continuous data, the continuous scatterplots and continuous parallel coordinates are more suitable. In this work, we extend them to uncertain data. Additionally, we also extend fibers to uncertain data. If you are interested, come to our presentation.
CMED is a visual analytics framework for exploring medical image data annotations acquired from crowdsourcing. CMED can be used to visualize, classify, and filter crowdsourced clinical data based on a number of different metrics such as detection rate, logged events, and clustering of the annotations. CMED provides several interactive linked visualization components to analyze the crowd annotation results for a particular video and the associated workers.
Programmers often make mistakes like this. ABS function is incorrectly called with a string. A programming language can catch such mistakes early on, but for this, it needs a type system. We present Typical, an interactive visualization tool for programming language designers. Typical allows them to explore common function type signatures and helps create a type system.
How many clusters can you see in these images? With different visual encodings in scatter plots, our perception of cluster count changes. We developed models that consider how visual density influences cluster perception. Further, we demonstrate using a threshold plot to optimize the saliency of clusters.
Tableau helps you see the stories in your data. It's designed to help you be smarter, so you can make better decisions faster. With Tableau, you can keep on asking questions in the data until you discover the root cause. Share your analysis securely. Your entire organization can access these interactive dashboards from any browser or mobile device to find their own answers. Tableau. Answer questions at the speed of thought.
The daily work of criminalists consists of analyzing relationships in complex data while proposing and verifying multiple hypotheses, often under heavy pressure. This poses high demands on their memory and cognitive capacity. We present Visualant, a tool that helps investigators track their visual exploration and reasoning. It organizes analytical state in a graph structure which can be revisited and shared with colleagues.
Program developers spend significant time on optimizing and tuning applications. But working with binary code to understand what compiler optimizations were applied can be challenging. We present our visual analytics system, CCNAP, designed to identify and assess compiler optimizations in binary code. Check out our paper to learn more.
In a visualization, laying out labels to data points needs to be done automatically with a fast labeling algorithm. We introduce occupancy bitmap. It's a data structure that helps the labeling algorithm to, first, quickly record the positions of existing marks and labels, and second, quickly detect overlapping of labels to the recorded positions.
In our paper, we address the problem of navigating complex multiscale and dense environments, such as these molecular models. We present a technique for browsing a model by clicking on textual labels, which we call hyperlabels. This allows the user to intuitively navigate the hierarchical organization of the model. For more details, read our paper or watch the talk.
After determining the departure timestamp, the experts then moved to verify the recommended shuttle stops and routes. Note that ShuttleVis recommends the default shuttle stops and routes based on the metric of average distance. Then they observed that in our cluster 4, the system recommends Xiong as the shuttle bus stop, but the experts identified that another drop-off spot Panshan is located in the middle part in this regional cluster.
In visual multivariate analysis, we often want to find out how the variables in the set relate to a particular target variable. Imagine we have medical data from patients that suffer from a specific disease. Then we might like to understand which conditions predict a more severe progression of the disease. This is a challenging task because the explanation could involve a specific combination of several factors. We propose a novel method based on neural networks to visually explain relationships in multivariate datasets that can also recognize more complex, nonlinear correlations.
We present TransVis, a design study that is proposed to analyze and integrate close and distant reading of multiple translations. TransVis presents the overview of the collection to capture global patterns that is facilitated by the ADM-VIV matrix. TransVis integrates a detailed view to explore interesting path of alignments. We also propose the TLC view to examine and explore the terms of the user selected path to justify and reason the AD analysis.
Attention mechanisms have greatly improved the performance of many language models, yet with great power comes increased complexity. In this work, we present attention flows, a visualization that let users interpret the language model's decisions and gain insights into the underlying self-attention mechanism. We also support model comparison that helps to fill the gaps between models in different training stages.
Imagine you have tons of text data to analyze. And you want to get an overview of your data, but traditional topic modeling techniques such as LDA are not working for you. Then, why don't you try Architext? We introduce a scalable and flexible way to interactively build hierarchical topics.
Digital humanities present great opportunities for testing new visualization approaches and evaluation techniques. However, and given the diffuse character and novelty of the field, it may also be intimidating for novel and senior researchers willing to get started in the discipline. In this paper, we propose a data-driven analysis of visualization for the digital humanities to identify key themes, authors, and relevant publications. So if you want to know more, please read our paper.
Due to the lack of efficient tools, traders rely on their memory to manually compare the algorithm instances of a trading algorithm. We work closely with the industry practitioners to discover the user requirements and develop a visual analytics system, TradeOut, for trading algorithm optimizations. Structured expert interviews are conducted, and a representative case study is documented for illustrating the system effectiveness.
String graphs are variants of stack graphs with curve-based line, and the main factor affecting its readability is the sign allurance through a perceptual inconsistency of the orthogonal and vertical direction. Aiming at reducing its impacts, we revisited the baseline formulation and proposed the concept of composition to help the string graph layout optimization. The result shows that our algorithms perform better than the others.
Entities and their changing relationships can be modeled more precisely as temporal hypergraphs, but hypergraph models are difficult to explore and refine. By leveraging domain-specific geometric deep learning models and a new multi-level hypergraph visualization, our technique allows for the direct integration of domain knowledge into the machine learning process. The multivariate hypergraph model structure can be analyzed on different abstraction levels. Simultaneously, experts can integrate their domain knowledge on the fly, and then explore the refined machine learning model.
Taylor-Coyer flows is a turbulent fluid motion created in the gap between the two rotating cylinders. The traditional reason-based methods are only able to capture the small-scale coherent structure. The detection of the large structure depends on the 2D cross-section, which is not the true configuration. We adapt the feature-level set methods and the density estimation to combine multiple attributes and use them as the filter to separate large and small-scale structure.
Visualizing streaming of big data may be difficult if the visual idiom gets cluttered. Although some techniques solve this issue by aggregating data into different idioms, each representing a different period, they still lack transitions to help people understand how data points get from one visual idiom to another. To solve this issue, we proposed several transitions between several pairs of visualizations. We tested them through a user study where participants watched a video per transition and had to answer 7 questions.
We present VIS, a tool for visualizing hypergraphs where edges can connect any number of nodes. VIS is the first technique to display hyperedges with no overlap or crossing. Vertices are represented as rows, time periods flow from left to right, and groups can be shown on the left. We designed the layout for readability. VIS shines with mid-size hypergraphs and it allows detailed analysis. We tested VIS successfully using publication datasets and data from historical documents.
Nowadays, online services are used for all kinds of activities. Strategies to increase the situational awareness of personal data stored by online services are needed. We present Transparency VIS, a visual, interactive web application. It allows common internet users to explore their personal data exports, which can be requested from online services like Facebook, Google, Instagram, or Twitter. Feel free to try it out online.
Data videos are quite popular nowadays. They usually show changes in the data. However, creating a data video requires multiple skills, and the process is usually laborious and iterative. Our approach focuses on automatic and interactive visual enhancement of important changes in time series data with data video.
When developing a deep learning model, people typically struggle to optimize hyperparameters that are affecting the model performance. To relieve the pain of this manual trial process, AutoML has been developed as a solution. However, to maximize the potential of the AutoML, people should identify a good AutoML setting for their task. Hypertendril helps to maximize the potential by visualizing AutoML algorithm behavior and guiding effective hyperparameters.
How do we represent remote users in synchronized visualizations while supporting divergent exploration? We present cursors, the basic unit of user representation in a collaborative visualization. They can vary significantly in appearance, as you can see. Cursors enable collaborative interaction techniques, such as peeking, tracking, and forking. To learn more, please read our paper representing real-time multi-user collaboration in visualization.
White space surfaces are a novel approach to convey depth in vessel visualizations. The core idea is to shift all additional depth cues away from geometry and to use the usually empty space between the vascular structures. This allows us to display functional parameters on the surface and supporting cues on the background. We will explain how to generate such surfaces and how to use them as a canvas to further enhance depth and shape perception.
We propose an interactive ensemble analysis framework that provides flexible interactive exploration of the ensemble data. Time series characteristics of data can be obtained by fast browsing time steps. The region stability heatmap view shows the stability of the selected region and provides region adjustment by directly clicking.
In this talk, we introduce CallFlow, an interactive visual analysis tool that provides a high-level overview of performance profiles from large-scale scientific applications. CallFlow visualizes the flow of resource of a program execution as a Sankey diagram to detect performance bottlenecks in parallel codes. CallFlow simplifies these calling context trees based on semantic information by constructing supergraphs.
While meetings are an essential part of everyday business life, most calendar visualizations are not designed for retrospection. We present a tool consisting of 4 coordinated views that integrate into the user's daily workflow and are designed to promote self-awareness about past scheduling decisions. We discuss the insights gained from an internal user study and from a field deployment. We also discuss how we strongly inherit from the principles of personal visual analytics despite targeting a professional environment.
Druid.js is a JavaScript library for dimensionality reduction where we implemented 11 DR methods. A typical use case for Druid.js is a web tool using DR. You just need to import Druid.js, create a DR object, and then call the transfer method. That's it. See the talk, the paper, or the supplemental material for more information.
Hurricanes, air pollution, forest fires, urban sprawl, ocean plastics, politics, traffic jams, and pandemics. So many of our modern challenges are geospatial, and so much of our big data is geospatial. How is the VIS community addressing needs to visualize and analyze this data? Our review examines IEEE VIS's recent contributions to geovisualization and geospatial analysis.
Hands-on cybersecurity training represents a domain where visual analytics can significantly improve the impact of teaching process. We describe this new application domain and introduce a conceptual model that can serve as a framework for the development of analytical visualizations. Unified training lifecycle will be discussed from the perspective of different user roles.
Tableau helps you see the stories in your data. It's designed to help you be smarter, so you can make better decisions faster. Connect to the data you care about. Sort, highlight, drill down, or filter your data in seconds. Add calculations to extend your data. With Tableau, you can keep on asking questions in the data until you discover the root cause. Tableau. Answer questions at the speed of thought. Tableau helps you see the stories in your data. It's designed to help you be smarter, so you can make better decisions faster. With Tableau, you can keep on asking questions in the data until you discover the root cause. Share your analysis securely. Your entire organization can access these interactive dashboards from any browser or mobile device to find their own answers. Tableau. Answer questions at the speed of thought.
we propose X-matrix, a novel method for random forest interpretability. From a random forest model, a logic rule is extracted from each decision path on every decision tree. Once the complete set of logic rules is obtained, visual representations can be built for global and local explanations. X-matrix, making random forests interpretable.
Hello. Student competition is intrinsic to the pedagogy of cybersecurity education. At RIT, we have observed that the collegiate penetration testing competition and other related competitions are missing a key element: visualization. In this position paper, we provide an architecture and plan to create compelling experiences for participants and spectators. In doing so, we can potentially attract new talent into the field.
Good morning, and welcome to the session on perception in color at VIS. One of the things that we'd like to know about this session is that apparently we have the most papers with transparent research practices. 4 out of 6 papers shared their methods and their materials. Some shared reproducibility materials. And so that's a very good sign as we move forward for trying to validate research methods. So we have 6 very interesting papers today. And we're going to start with the paper in Semantic Discriminability for Visual Communication, and it will be presented by Karen Schloss. Karen is an assistant professor at the University of Wisconsin-Madison in psychology. And take it away.
Hi, my name is Karen Schloss, and today I'm going to talk about semantic discriminability for visual communication. Optimizing palette design for visualizations requires balancing many factors, including perceptual factors, semantics, naming, aesthetics, and affect. Sometimes conflicts arise between these factors, and so we have this general question of how do we navigate trade-offs when trying to optimize color palette design. Today we're going to focus on perception and semantics in particular. Within the visualization literature, there's been an emphasis on perceptual discriminability. And this makes sense because if two colors appear the same, they simply cannot communicate different meanings. But if colors appear different, should we prioritize perceptual distance? Or can we relax constraints on perceptual distance to maximize other factors? And the factor we're interested in today is semantic discriminability. Semantic discriminability is the ability to infer a unique mapping between visual features and concepts based on visual features and concepts alone, irrespective of the encoded mapping in the legend. Using this as an example, let's say these two bars represent banana and blueberry. You can easily infer that banana is yellow and blueberry is blue because banana is more associated with yellow than blue and blueberry is more associated with blue than yellow. Now, in the encoded mapping, it could specify that banana is yellow and blueberry is blue, or the opposite. And your ability to interpret the visualization will depend on the degree to which the encoded mapping matches your inferred mapping. But for now, we're focusing on the inferred mapping when talking about semantic discriminability. Now, this is a case of high semantic discriminability, and we can contrast this with the case of low semantic discriminability, where both colors are strongly associated with both concepts. So the ability to infer a unique mapping between visual features and concepts in this case is weaker. Conflicts can arise between perceptual and semantic discriminability. Let's look at some examples. Let's imagine I'm going to show you some graphs, and your task is to indicate which color encodes watermelon and which one encodes mango. When perceptual and semantic discriminability are low, it would be pretty hard to do this task. And when they're both high, it's probably pretty easy. You can infer that the bar on the left is watermelon and the one on the right represents mango. Now, if we make perceptual discriminability high and semantic discriminability low, it might be harder. And the key question is what happens if we make semantic discriminability high but perceptual discriminability low? This brings us to our general research questions. Firstly, does semantic discriminability influence interpretability independent of perceptual discriminability? And if so, when they conflict, which factor dominates? We addressed those questions in the following experiment. Participants were presented with trials that looked like this. There was a bar graph with two colored bars and a fruit described at the top of the screen, and their task was to indicate which color represented that fruit. There was no legend, so participants had to rely on their inferred mapping to do the task. We tested 8 colors, which were selected based on color concept association strengths with our two possible target fruits, mango and watermelon. These are those association strengths. So we can see that the 4 colors on the left are associated with mango and not with watermelon, and the 4 colors on the right are associated with watermelon and not with mango. And I'll mention that these association strengths were obtained from different participants than those in the present study. The design included all combinations of 2 possible targets, mango and watermelon, 28 color pairs, which was all pairwise combinations of these 8 colors. We left-right balanced the position of the colors. We also balanced the position of the bar heights, which was taller. And we had 3 repetitions for each one of these types of trials, which produced a total of 672 trials, which were done within subject. As I mentioned on the previous slide, there was no legend, and so there was no objectively correct answer from the perspective of the participants. But we can define accuracy as optimal assignment in an assignment problem. Here I'm showing you an assignment problem for mango and watermelon, where mango is capital M and watermelon is capital W, and for 2 colors. And the thickness of the edges represents the mean association strength between each pair of concepts and colors. To solve the assignment problem, we look at the sum of the outer edges, and we subtract the sum of the inner edges to see which is greater. If this difference is greater than 0, that means the outer assignment is the solution, and if it's less than 0, then it's the inner assignment. For this particular pair of colors, that means that if participants were presented with these trials, brown would be the correct answer for mango, and green would be the correct answer for watermelon. Our goal is to predict patterns of accuracy, and we want to do this based on perceptual discriminability and semantic discriminability. And so we operationalize those measures as follows. So perceptual discriminability is perceptual distance, or delta E, which is just Euclidean distance in CIE-LAB space. Semantic discriminability we define as semantic distance, or delta S, which I will explain over the next few slides. When talking about semantic distance, we're going to bring back our assignment problem from before. Now, if we were to add noise into the system solving this problem, so we were to perturb the association strengths, we would get the same answer most of the time for this particular assignment problem because there's a reasonable difference between the association strengths for the outer edges and the inner edges. So we call this a robust assignment problem. We contrast this with an assignment problem like this, where now the outer edges are the same, but now we have two new concepts, concept A and B, and the inner edges are now stronger. And so if we were to add noise into this system that's solving the assignment problem, then you could have cases where you get the inner assignment as a solution rather than the outer assignment. So we would call this a fragile assignment. When computers are solving assignment problems, there's no difference between these two conditions. They solve assignment problems in a deterministic way, which means that they would come up with the same solution for both of these cases, because in both cases, the sum of the outer edges is simply greater than the sum of the inner edges. But when humans do assignment inference, when they're inferring mappings between visual features and concepts, they do this in a probabilistic way. And that's because human color concept associations are noisy. And this is relevant to how we define semantic distance. So when defining semantic distance, instead of thinking about just the mean association strengths represented on the edges, we're now going to think about distributions of association strengths. And when solving the assignment problem, you can think about this as summing the outer distributions and subtracting the inner distributions. In this combined distribution, area to the right of 0 means that the outer edges are the correct assignment, and area to the left of 0 means that the inner edges are the correct assignment. So we define semantic distance as the absolute distance of area between the left and right side of this distribution. Let's take a look at semantic distances of our particular colors. Here on the y-axis, I'm plotting semantic distance, where 0 means smallest distance and 1 means largest distance. And we're looking at this for each of our 8 colors. To remind you, these are the color concept association strengths for these colors. So the order on the x-axis here is that the colors on the left are the colors strongly associated with mango, and they're increasing in association strength with mango as we move outward. And the colors on the right are strongly associated with watermelon, and they're increasing in association strength again as we move outward from the center of the x-axis. Here I'm showing the semantic distances for color M1 paired with every other color. And the graphs above each one of these points represents what a trial would look like for M1 paired with every other color represented on the x-axis. So that's the pattern for color M1. This is for color M2, and this is the rest of the colors. So this pattern of semantic distances is a property based on the color concept associations of these particular colors and concepts. And so our question is whether human responses will look like this pattern. Now let's compare semantic distance with perceptual distance of the same colors. Here are the semantic distances I showed you before, and here are the perceptual distances. Overall, these two factors are uncorrelated, but there are some strong conflicts. Some pairs have high semantic distance and low perceptual distance, and others have low semantic distance and high perceptual distance. And it will be interesting to see how participants respond in light of these conflicts. So now we're going to put our perceptual and semantic distances off to the left. Before we look at the data, I just want to mention we have one plot for semantic distance for both mango and watermelon, and that's because these distances are determined jointly. And of course, we have only one plot for perceptual distance because it's just based on the pairwise distances for each pair of colors. But when we look at the responses, accuracy was assessed separately for mango and watermelon, so we'll see two graphs, one for each target concept. This is going to be the data for mango, plotting the mean proportion of correct responses, plotted in the same way as semantic and perceptual distance. The solution to the assignment problem, so the correct answer would mean responses around 1. Of course, we would expect some noise in human responses around 1. But if there's systematic variability in the pattern of responses away from 1, then the question is that predicted by semantic distance or perceptual distance or both? Here's the data for mango, and we can see there is systematic variability away from just correct answers near 1. And this is more similar to the semantic distance pattern than the perceptual distance pattern, and we'll look at an analysis showing that in a moment. So that's our mango data. Here's our watermelon data. And we used a mixed effect model predicting these patterns of accuracies based on semantic distance and perceptual distance. Semantic distance was a significant predictor where larger distances led to greater accuracy. Perceptual distance was a marginal predictor, but it was in the opposite direction than what you would expect. Actually, smaller perceptual distances resulted in greater accuracy. And that's because of those conflict cases I mentioned before. So here we've got cases where there's a high semantic distance and low perceptual distance, and we can see people are super accurate for those trials. But when we have low semantic distance and high perceptual distance, responses are closer to chance. Now you might be noticing the mango data and the watermelon data look kind of different from each other, and we wouldn't expect those differences based on semantic distance and perceptual distance alone. So what can account for these asymmetries? Well, if you recall, they have very different patterns of color concept association strengths, and we know from prior work that association strengths do predict accuracies in these types of data. So in the next model, we included these association strengths in addition to semantic distance and perceptual distance. Association strengths were a significant predictor, again, as were semantic distance, and perceptual distance, again, was not significant. We can look at the regression predictions based on that model, and those are strongly correlated with the pattern of responses. So that means that we can strongly predict patterns of accuracies based on semantic distance and association strength. And again, perceptual distance was not a significant factor in this model. So in conclusion, I'm going to bring back this 2x2 we started off with in the beginning. We can see that when semantic discriminability is low, people are basically near chance. But if semantic discriminability is high, even if perceptual discriminability is pretty low, people are similarly accurate. These results suggest that semantic distance influences interpretability independent of perceptual distance, and when conflicts arise, semantic distance dominates interpretability. And finally, these results suggest it can be worth relaxing constraints on perceptual distance when navigating trade-offs for optimal palette design. I would like to thank my co-authors on this work, members of my lab and my funding sources, and thank you for your attention.
Okay, so thank you very much for a really interesting paper. As you can see from Discord, we had a number of questions. So I'm going to start with a question posed by Danielle and Maureen, which is, where might a more generic color name distance lie with respect to the space formed by semantic versus perceptual distance?
So I think this is an excellent empirical question. I think I would love to compare what name distance metrics would predict based on, or with respect to what semantic distance would predict. But I will say that semantic distance can operate on any colors and concepts, even if the colors are not assigned to a given name. So for example, you can calculate the distance, the semantic distance between two colors and concepts that no one would ever name that color with that particular concept, because you can get people to rate association strengths between all colors and all concepts, and they do give systematic ratings. So I think there could be a lot of overlap between semantic distance and name difference or name distance, and I would love to explore that with one or both of you. But I think that there is some cases where semantic distance might get a substantive power where name distance might not.
Okay. So there are also questions arising about, is there a cultural influence, or more generally, what happens when the semantic associations are more nuanced? Joe Wood asks, for example, what color is an apple?
Sure. So firstly, I will say, so apple is a case where we've got a multimodal distribution, so is watermelon. Granted, you also have the apple product versus apple fruit. And so the semantic context, I think, is an important thing that is obviously not something that we tackled in this particular study. The cultural question is extremely interesting. And the idea is that semantic distance is calculated based on association strength. So if association strength is the same across different cultures, semantic distance will be the same across different cultures. But if association strength differs, semantic distance will as well. So what that means is that if you go to a particular audience that you're interested in creating a visualization for, and you can represent what their association strengths are, then you can calculate semantic distance for that particular audience. I mean, at least we find that we get similar association strengths within different populations within the US, but of course, across different cultures, there could be a lot of variability in that. And that's the really cool aspect of this kind of approach, is that all of it is based on the input, which is association strength. So once you quantify that, a whole lot falls out of that in several lines of the work that we're doing in my lab that I didn't have a chance to talk about today.
Right, so I would continue this with one more question, which has to do with this general idea of semantic resonance. And that is, what about things that are more difficult to measure? Is it that you have to actually calibrate and determine what the semantic resonance might mean for more abstract concepts before you are able to provide the design guidelines for a particular audience?
So as I understand it, semantic resonance is the degree to which a particular, at least as it's defined in the paper, is the degree to which a color evokes a particular concept. And so the work that we've been doing in our lab shows that people can infer mappings between colors and concepts, even though individual colors don't evoke that particular concept. And we can predict that well based on the relative association strengths between all colors and all concepts in the encoding system. And we call this process assignment inference. So I think, again, if you can quantify what those association strengths are, you can predict those. Sorry. And technology. And we find that people do have systematic associations for very, very abstract concepts. And there's new work that's coming out of my lab with Kushin Mukherjee, where we're finding really cool, robust associations for very abstract concepts, and we can predict them in really cool ways. So stay tuned for that.
Thank you very much. Please continue the discussion on Discord, and we have to move to the next presentation.
Thanks, everyone.
Yes, so we're going to introduce the next presentation. I'm sorry about this. I've just been told that you could see comments in the reflection of my glasses. So the next presentation is going to be done by Khairi Reda, and it's on Rainbows Revisited, modeling effective color map design for graphical inference.
My name is Khairi Reda, and I am with Indiana University at Indianapolis. And I'll be presenting our work on modeling effective color map design for graphical inference. This is joint work with Danielle Szafir, who's at the University of Colorado Boulder. Color maps are very useful for analyzing quantitative data such as scalar fields. And the idea is that instead of looking at arrays of numbers, we can look at colorful images such as this one. Now, with an image like this, I should be able to do a number of things. So for instance, I could pick a location of the map and try to estimate the value at this location graphically. So this is a task that I could refer to as a single percept task because it involves a single location or a single feature within the image. But there's also more complicated tasks that involve multiple percepts that people often try to do with color map data. So for instance, taking these 3 simulations, I should be able to conclude that the ones on the left reflect mostly the same outcome or same output versus the one on the right here, which seem to reflect a different behavior or a different observation. Now, in deciding what color map to use for these kinds of tasks, we could turn to the guidelines. And one of the first things that people often mention is that we should select color maps that are smooth and perceptually uniform, such as this VIS color map that you see here. By the same token, people often sort of discourage the use of color maps that exhibit some kind of a banding or color categorization. And for instance, this rainbow color map is often thought to be a bad choice because it exhibits a sort of a sharp boundary, particularly in the yellow region. So this is something that often is discouraged within the literature. But in looking back at what kind of tasks that these guidelines have been tested on, we find that mostly they've been tested with relatively perceptual and single percept tasks. It's unclear if they do generalize to these more interpretive tasks where people are asked to operate on multiple datasets or multiple percepts and synthesize a judgment across multiple features. Now for this kind of work, we're sort of coming with a somewhat of an unusual or a perhaps even a contrarian hypothesis. So we're conjecturing that color categorization or color bands can indeed help in these tasks, which require inference across multiple percepts. And the rationale behind this is that the color segments that we often see in things like the rainbow can in fact aid the visual system by helping us extract summary features and statistics from the data with relative ease. So for instance, I can attend to the red regions here, or red patches. I can switch my attention to the blue regions, and I can try to estimate the apparent size, frequency, or distribution of these features, and perhaps even compare those distributional statistics to a different image. And with that information, I can probably make some sort of an inference about the nature of the data in these 2 visualizations. But in addition to sort of facilitating this kind of ensemble perception, color segments can help us compare individual features within images. So for instance, I can turn my attention to the red hotspots here and compare their shape within these 2 images. I can perhaps switch my attention to the green areas or even to the blue halos that are surrounding them and try to make some sort of a comparison between these 2 data sets. Now you might find that this is a little bit trickier to do with a color map that exhibits less categorization. And the reason for that is there will be less discrete features to attend to within the image, which could make the task theoretically a little bit more difficult. Now, in order to test this hypothesis, we needed an appropriate task. And so we settled upon graphical inference as a useful task to operationalize in this study. And so the idea here is that we present the viewer with multiple plots, and we ask them to essentially pick the one that does not belong. And in this particular instance, that would be the one that's highlighted in red, particularly due to these outliers that are in the middle of the model. So in picking the correct answer here, the viewer would have essentially discriminated between 2 models. One is a target, and another model is the one that's highlighted in blue, which is represented by these 3 different decoys. So this is a task that essentially involves comparing multiple visual features, but also involves making a summary determination or a judgment across these features. Instead of scatter plots, we adopt scalar fields, particularly ones that are encoded in a color map. So here's one example of stimulus from our experiment. The correct answer here is the plot that's highlighted in red. This is the same stimulus encoded in a different color map, and particularly in a rainbow type color map that exhibits a little bit more categorization than VIS. And the correct answer is also highlighted here. So to give you some background about how we generated these stimuli, We start with a target model that is composed of a number of 2D Gaussians. We integrate those kernels and we sample them and we obtain one plot. We perturb those Gaussians a little bit and get a decoy model as a result. We sample the decoy model 3 times and we embed the results along with the target sample and present them in one lineup to the participant. And so, of course, the correct choice would be the plot that has been sampled from the target model. Now, we also needed a way to distinguish between, or to measure the level of color categorization that different color maps exhibit. And for this, we came up with a new metric that we are going to call color name variation. And so the idea behind this is to simply count the number of distinct color names that appear in a continuous color map. And so for this reason, we use a probabilistic color model by Hare and Stone. And with something like the rainbow, we get probabilistically about 4.78 colors that are mixed in within this ramp. For something like Viridis, there's less color variation, or less color name variation. So we get a score of 2.75 for this particular scale. So for our experiment, we select a set of 12 color maps representing different design families. And our hypothesis will be that color maps with high name variation will enable more accurate graphical inference. And according to this hypothesis, we actually don't need to care that much about the design family. Rather, all we have to do is order them by their color name variation. And according to our hypothesis, this metric will also be correlated with accuracy. And in fact, this is precisely what we see in the data. So we see a clear correlation between name variation and performance or accuracy in graphical inference. So on one end of the spectrum, we have rainbow color maps, which have which cross a high number of color names. So they have a high color name variation, and they also score pretty highly on this test. Single hue color maps are on the opposite end of the spectrum, and those are the maps that have fewer color names, and their performance was also much less. And somewhere in the middle, we tend to find multi-hue and divergent ramps, which tend to mix, and their performance also seem to be correlated with the number of color names that is packed within each ramp. So in summary of the first experiment, what we find out is that accuracy in graphical inference was linearly correlated with the number of distinctly nameable colors in a specific ramp. And we found that the more colorful maps tend to perform better. So the top performing color maps were a traditional RGB rainbow, jet, and plasma, which incidentally packs in a little bit more color names than other multi-hue ramps. So these results do indeed support our first hypothesis. Now, as useful as color bands or color categorization can be for inference, we also have to consider the alternative hypothesis that they can also cause people to infer false features. And this is particularly sort of true for rainbow color maps, which tend to imprint these highly visible boundaries that are not necessarily within the original data set. And so we wanted to see if these more colorful maps can indeed trick people into reporting false differences that are not due to the model. So what we do is we adopt the same task from the first experiment, but we add a fifth option for participants to declare that there's no difference between these images. Now, 50% of the stimuli are in fact true positives, meaning there is a plot that is unique or different. The other 50% are true negatives, where the plots are sampled essentially from the same model, and there's no decoys, and the correct answer would be to declare that there is no discernible difference between the images here. And so what this allows us to do is look at specificity and sensitivity separately. So when we look at the specificity, which is the true negative rate, what we find is that there's essentially no correlation between color name variation and specificity. So that means the more colorful maps are unlikely to result in more false inferences or false positives. On the other hand, when we look at sensitivity, we do again find this relationship between name variation and sensitivity. So color maps that have a higher number of names will be more sensitive for, at least in the context of graphical inference tasks. So in summary, we've introduced a new metric we called color name variation, and we found that it actually predicts performance in graphical inference. Ultimately, the more colorful a color map, the more accurate it is in this specific task. Now, what's interesting is that the highest performing color map don't have to be always rainbows. So plasma, for instance, is a multi-hue, and it's perceptually uniform, yet it's among the top 3 sort of performers. And we also found that plasma is incidentally more accurate than Veritas, even though they share a lot of the similar design properties. But incidentally, plasma had a higher number of nameable colors in its composition, which, as our model predicts, essentially leads to better performance. We found out that traditional perceptual properties like uniformity or lightness, monotonicity don't seem to affect performance as much in graphical inference. These 2 points may, in fact, explain why people still prefer to use a rainbow color map, for instance, or a more colorful map when analyzing particularly scientific data, as these maps seem to have some advantage in graphical inference. One heuristic to design appropriate or good color maps to facilitate inference is to essentially maximize the color map's curve length in lab space. The details are in the paper, but to keep it short, we found that this metric can indeed well approximate color name variation. So in closing, I want to point out that the data and materials for this paper are available if you're interested at this link. And I do want to acknowledge funding from the National Science Foundation as well as from Argonne National Lab. And so with that, I'd like to thank you for listening to this presentation.
So thank you for a very interesting, excuse me, thank you for a very interesting paper, and it certainly generated a lot of questions on the chat. So let me just start with a few and encourage those of you to continue the discussion on Discord if we don't get through them. I'm going to start with questions that have been posed by both Steve Harrells and Bernice, which is, was the nameability property differentiated from the number of discriminable steps in the color ramp? That seems like a pretty big confound. There's concern that nameability, discriminability, and segmentation spacing don't appear to have been manipulated independently.
They're not, because discriminability, or essentially perceptual distance, is correlated with name difference. So we can't manipulate both separately, but nameability does have specific, at least we had a pretty good theory on why nameability would matter here, and so we went with that. But in the paper, we do test an alternative model that is based on lab distances. So, so I suppose both factors predict performance in this case.
And so more generally, can you speak to the issue of feature selection, which is an attentional function, as opposed to ensemble coding?
Yeah, so that's an interesting question. We really can't explain which one is more dominant in this experiment. So it could be a function of being able to attend to individual features by essentially sort of tracking them by name. So you could
Hi
track
everyone, my name is Pascal.
The green features separately, compare them across the images. It's also possible that you may be able to perform some kind of ensemble perception where you can estimate the sort of the blobbiness or the size of the different patches with a glance, and then use that as some sort of a statistic to help you differentiate between different models. We really don't have an explanation of which one is sort of more likely this experiment. I think both are potentially good candidates, but I suppose so this is something that we can try and test and tease out in future studies.
There are a lot of follow-on questions with this, so please go back to the Discord to discuss it, but I'd like to get another two questions in. One is Jason talked about the utility of the shape perception depends on the extent, depends on the scale, right? In other words, if features are consistent across scale, then they're probably less prone to getting hidden by varying the color map. Can you speak to that?
So what we did is we generated these random models, and these are combinations of mixtures of Gaussians. The result is that some of the features or some of the discriminating features are small, some of them are larger, some of them are peaks, some of them are kind of like what you might call the negative space in between the Gaussians. So we didn't control for that, rather we tried to cover a broad range of features that might arise randomly. But I suppose the feature size could definitely be a factor if you kind of focus on that one alone. There is some work by Colin and colleagues that shows that there's a threshold for detecting different features of various sizes. In our study, we just confirmed all of those and generated features of various sizes by just using random models.
So thank you very much for interesting answers. There's a host of discussion on Discord, so I think you're going to be very busy for a while.
Yeah, thanks so much.
So, thank you. Now, we've heard about people testing color maps. Now we're going to hear about an actual test bed, a testing environment for continuous color maps. And this is going to be presented by Pascal Nardini. Pascal is a PhD student at the Institute of Computer Science at the University of Leipzig.
Hi everyone, my name is Pascal Nardini, I'm from the Leipzig University and I will present our work, a testing environment for continuous color maps. Let us begin with the motivation. We are not in school, it's not cheating to overlook what others do. In many other fields in the computer science, algorithms are commonly evaluated using open libraries of predefined tests. In the visualization community, the evaluation or comparison is often made with usability studies. There are some reasons why we thought it would be nice to have some test functions for evaluation too. First, two big reasons, money and time. Let me explain. This researcher wanted to do a user study. He has to organize the probands, devices and also a location. Additionally, he also needs a detailed plan, guide, checklist and so on. On the other hand, if he had a task which he could evaluate using test function, he could save some of these points. Further reasons for the test functions are the repeatability and the comparability. If a scientist wants to repeat a user study, he has to do all the work again. With the test function, he could easily just repeat the test algorithm. Comparability. A scientist from a big lab introduced a new algorithm and has made a user study with a lot of domain experts. A few years later, a student developed an alternative algorithm and wanted to do a user study and compare it with the old one. He has to attract other students with chocolate to be part of his user study as volunteers. Should he compare his study with the old one? I don't think so. And there are more factors that could affect the results, like for example the lighting conditions or the use of monitors with different color reproduction. Don't understand me wrong, user studies are very important, especially in view of usability or general considering the human factor. But sometimes an alternative could be helpful. For example, to test the first version of an algorithm and do the user study with the final one. Therefore, we want to initiate with this work the development of test functions, and we start with color maps. We hope we can also animate other fields of the visualization to think about this idea. Now I want to tell you more about the tests. We try to offer a large selection and consider many scalar field attributes which can be interesting. We start with a few global variables which are part of some test functions. With the both R variables, the user can determine the range of the test function. It is not defined which one is a larger or smaller one. The minimum small m and the maximum great M are defined by these two R variables. The variable b is always an user-defined exponent. If a test function has different options, the user can select one with the type variable t. We start with the local attributes. Because time is short, I will give you here only a general overview to each test and will not explain all equations in detail. Some popular test images in the literature use steps between the adjacent pixels. Therefore, we developed the step function. We designed a grid where each value of a set A is adjacent to each other. We archive this with two types of alternating rows. For one row type, each row containing one single value, and that in increasing order. The other one containing all values. At this slide you can see how an example with 4 steps would look like. To increase the imagination, we also offer height maps at our tool. We continue with gradients. At the gradient test function, the user can select types to determine the process along the x and y axis, which can be different. He has the options linear, concave and convex. For the linear option, the exponent b is always 1. The gradient test function uses the function g to control the process along the y-axis. The rest of the function controls the process along the x-axis. If the user set for the small r variable a smaller value than for the big R variable, we get an increasing gradient function. If not, we get a decreasing one. As next, local topology. I think at this slide I don't have much to tell. We use the well-known formula to create a minimum, maximum or saddle point. With the variables O and P, the user controls the result of this test function. Another attribute of scalar fields are ridge and valley lines. We designed this test function so that we have always a ridge or valley line at x is null. Like at the gradient test, the user can select a type to control the process along the x and y axis. For the y axis types, nothing changed, and we used here also the same function g to calculate their process. In contrast, the types for the x axis look a little bit different. We mirrored the process along the x axis at x is null. For a better imagination, you can see here the 3D height maps for each type. With the mirroring, we were able to create the ridge and valley line at the exact position x is null. Like mentioned before, I will not talk detailed about the equation, but for those who want to pause the video later, here it is. If the user set a smaller value for the variable small r than for the big R, the function creates a ridge line. The other way around, it will create a valley line. Part of recording data, or rather signals, is always the frequency. This was the motivation to create a frequency test. We designed this test so that the frequency increases along the x direction. We start with a single sine wave with the frequency 1 at x is null. The width in x direction depends on the harmonic series and the user-defined number of frequency increases. The user set also the median u and an amplitude w. With the 1 minus y after the w in the equation, we cause a gradient that approaches to the median along the y-axis. Here you can see an example image. The height map on the right side is a screenshot from the back. Here you can see how the waves get closer to the median u. In many scientific fields, natural thresholds like the freezing point of water and the data distribution close to them are of significant importance. So we created a test function to test thresholds. The user determined a threshold t between the test function minimum and maximum. Next to that, he can also set a type. He has the options between linear, flat and steep. These types describe the behavior of the gradient around the threshold in the middle of the test field. Like at the frequency test, the threshold test function approaches to the threshold into the y direction. Because the threshold t can be any value between the maximum and the minimum, we need here two equations to describe the process along the y-axis. The function small m for the x values less or equal null and the big M for the x values larger than null. Here you can see an example for each type and additional the according height map visualization. Sometimes small value changes also can be significant, important. And the user wants to know if these small value changes are recognizable. Therefore, we designed the little bit test. The idea is to have a linear gradient from the minimum to the maximum in y direction. Then we create grooves with different depths so that we have alternating the original gradient and the groove. The user defined a groove minimum as start depth and a groove maximum for the last groove depth. Groove depths between them will be calculated with linear interpolation. For the realization of the grooves, we use the sine wave. Here you can see an example where you can see the linear gradient into the y direction and the grooves, especially at the height map visualization. Next to all these local attributes of scalar fields, we also want to offer global attributes. With this test function, we want to create global topological structures with a large number of critical points. Our idea is simple. We use one of the mentioned or following test functions as a background, then we use a 2D version of the improved noise algorithm introduced by Perlin, which is often used for the creation of percentage textures or for the terrain generation in computer games, and add this noise to the background function. We offer 4 types for the addition process. The replacement option replaces the function value with the noise value. At the range scaled option, the change is related to the test function range. At the max scaled option, to the maximum value of the test function, and at the min scaled, to the minimum value. We also offer a clipping, so that the resulting values cannot leave the user-defined range. Here you can see an example. At the top is the original and the noise field, and below the 3 options. Another global attribute of data is a noise. Here we use nearly the same method. In contrast, we use a standard random algorithm from JavaScript. The user can set a proportion of affected pixels and also a distribution. We offer a uniform, a normal, a better left and a better right distribution. For those who want to pause, here I have an example with possible option combinations with a set proportion of 75%. To offer more opportunities for global topological structures, we also add an additional collection with test functions we found from other fields of the computer science. We also know that our test functions cannot replace data from the real world. Therefore, we also add a collection of real-world data from different sources. Now we have finished the test function chapter. Sorry, I know that it was a lot. We also work on methods to test the mentioned test function. One of them we have present in our work. I will explain this algorithm with an example. We start with a simple field you can see at the right top corner and we want to use a color map you can see above this field. With the field values and the color information we create 2 new fields containing values which represent the differences. For that we go through all pixels and the neighbors, calculate the value or color difference, identify the maximum and use the value as entry for the difference field. Next to the maximum value, we also implemented the use of median or the average value. With this method, we calculate the value difference field and the color difference field. For the color difference field, the tool can use the Euclidean distance in the lab or D99 space or the matrix DE94 or DE2000. If our color mapping is global uniform, the entries of both difference fields would contain the same information but with a different scaling. To check this, we normalize both fields using the maximum and minimum value of the fields. Then we subtract the color difference field from the value difference field. With the result, we can analyze the color mapping. With positive values, the color map would give an overestimate perception of the real value difference. With negative values, an underestimate perception. I show you this in a tool. We use a ridgeline test with added simplex noise. At the evaluation section, you can see the value field represented with a grayscaled image, the color mapping, the value difference field, the color difference field, and the result of their subtraction. Here you can see where this test identifies a disruption of uniformity. If you use instead a uniform color map, the result image is perfect white. For the future work, we plan to extend the collection of test function and especially the collection for the real-world data. For the second one, the best would be a database connected with a web interface where researcher can upload data. Next to that, we also want to do more research for the manual and automated analysis of the test functions. This is the end of my presentation. Many thanks for your attention.
Okay, thank you very much, Pascal, for an interesting paper. It's very interesting to have a possible test suite for those of us who work in color. I would ask you though, when you have done this, have you looked at this? You looked at it with respect to particular properties of the data that you want to elicit. However, have you done this with respect to the kinds of overall tasks in which people might be using the visualization, whether they need it to be highly prioritized or for at a glance, or whether they're looking at this as a focused task?
So we have done this on 2 tasks, and yeah, if a user want to do at the moment to do this test, he has to know what he want to show. So if you want to show frequencies or something like that, and then he had to made his own collection of these test functions, and then he can test these attributes he want to show with his color map. Yeah, so for the future, we also want to work more on the report. So we want to create a report. At the moment, we only have this this evaluation technique we use. I showed at the ending of the video. So we hope we can work there more on this type. So the evaluation of the test function is more for the specific test function and not a general evaluation method.
So we have a question from Bernice Rogowitz who says, is this tool available for researchers to play with?
Yes, it's available at ccctool.com. So at Thursday in the Intelligent Systems session, I also have a presentation about this tool. At the moment, you only can create this test function and not save it. So for the future, we also plan to create an export where you can export VTK files, or maybe also C++ code or something like that. So you can play with this test function by your own. Yes.
Yes, it would be great for color researchers to get their hands on it. If we have no other questions for Pascal, thank you very much. And we're all looking forward to seeing the demonstration of the tool on Thursday's presentation. And Sean has posted a link to this in the Discord.
Thank you very much.
Thank you. Thank you. So our next talk is moving away from color and looking at issues that arise with respect to shape in common charts. And our coming talk is called Truth or Square, Aspect Ratio Biases Recall of Position Encodings. And it's going to be given by Cristina Ceja, who is a 4th-year psychology grad student at Northwestern University.
Hi everyone, my name is Cristina Ceja, and I will be talking to you today about our project, Truth or Square, Aspect Ratio Biases Recall of Position Encodings. Here are just a few examples of the visual encoding channels commonly used in visualizations to encode data, ranked by how precisely they allow for comparison judgments. But perception and memory of these encodings can often be biased. For example, the circle in the United States here may appear darker than the one in Canada based on its surrounding colors, even though these circles are the same lightness. Similarly, the gray circles surrounded by these smaller black circles may appear larger than the ones surrounded by the larger black circles, even though they have an identical area. And although this vertical line appears longer than the horizontal line, they're actually the same length. So, if many of these encoding channels have been shown to be susceptible to bias, what does this mean for how we perceive or recall data values within the same charts that rely upon these encodings? Even in simple bar charts, our recall of data values can be biased in memory. In a recent study, participants were shown a single bar mark with a tall width to height aspect ratio and asked to recreate the vertical position value of the top of this mark from memory. But participants consistently underestimated its position. In a similar study, participants were shown multiple bars resembling a single mark with a wide width to height aspect ratio. They were then asked to recreate the average vertical position of the top of these bars from memory, but they consistently overestimated its position. Why does the direction of bias differ across these two studies? One possibility could be the result of categorical prototype effects. In the case of bar charts, you can represent the actual vertical position value of these bar marks in memory. However, your memory can be biased by a salient prototype shape, or a square with a 1-to-1 width to height ratio. And these two representations morph together in memory, resulting in a bias toward the prototype square. That means underestimation for those with taller width to height aspect ratios, and overestimation for marks with wider width to height aspect ratios. So in experiment 1, we tested whether the width to height aspect ratio of a mark interacts with the square prototype to bias position estimates. We manipulated the aspect ratio of the marks while holding the mark's area constant to determine the role of aspect ratio in this bias. We first showed participants a bar mark with either a wide, square, or tall aspect ratio for 0.5 seconds. Participants then viewed a visual noise mask for 0.5 seconds to avoid any potential after images that could affect their memory of the display. Participants then responded by dragging the top of a response probe, a bar with a wide, square, or tall aspect ratio, depending on the bar previously shown during the trial display, to match the vertical position of the top of the bar they had just seen. After participants dragged the top of the response probe to the desired position, they clicked the mouse to enter their response, and the next trial was initiated. As an example trial, here's a mark with a wide aspect ratio, followed by a visual noise mask, and the response, where participants drag the vertical position of the top of the bar to the desired position, and click the mouse to record their response. To measure bias, we calculated signed error with pixel values on the y-axis and the aspect ratio of the bar marks on the x-axis. Each dot here indicates the mean error for a single participant, and the annotated numbers are the mean error in pixels for all participants. So here we can see a main effect of aspect ratio, as marks with wide aspect ratios were significantly overestimated, while those with tall ratios were significantly underestimated. Marks with square ratios, however, were not significantly biased. And although bias is the main focus of this work, we also show the accuracy of these responses. Bar marks with tall aspect ratios were significantly more variable than those with square ratios, but there was no difference between marks with wide and square aspect ratios. And these data are consistent with the idea that the aspect ratio of a bar mark can bias position estimates, such that wide aspect ratio marks were consistently overestimated, but tall ratio marks were underestimated, and those with square aspect ratios were not consistently biased. All of which is consistent with the potential biasing effects of a categorical prototype of a square mark. And this is also particularly interesting because aspect ratio isn't intentionally used to encode data in bar charts. Rather, it is an incidental visual property of this chart type or a byproduct of the chart's design. Yet aspect ratio isn't the only incidental visual property of bar charts, as the bar charts that we typically encounter in the real world tend to also incidentally vary in area. But as we held area constant in experiment 1, we don't currently know what effect area could have on our memory for position in real-world bar charts, above and beyond aspect ratio. So in experiment 2, we question whether area, another incidental visual property of bar charts, can bias position estimates above and beyond aspect ratio. To test this, we ran a within subjects replication of experiment 1, in which the different aspect ratios all had an identical area, and compared that with a variable area condition to isolate any potential effects of area. In this condition, we held the width of the bar marks constant across the aspect ratios, resulting in different areas for the different aspect ratios. For the variable area condition, participants were shown marks that now had fixed widths and differed in area, followed by a visual noise mask, and then dragged a response probe to the desired position and clicked to record their response. We also included a direct replication condition of experiment 1 in our within subjects design that had stimuli identical to experiment 1 that varied in width but had a fixed area. Given that the design of this experiment is similar to experiment 1, I'll save us the time of going through an example trial and just jump directly into our results. For bias, we will start with the signed error for our replication control condition. We again found a main effective aspect ratio in the direct replication of experiment 1, as marks with wide aspect ratios were significantly overestimated, while those with tall aspect ratios were significantly underestimated. Marks with square aspect ratios were again not significantly biased. For the variable area condition, we see the same pattern of bias. Looking at accuracy or absolute error for both conditions, we also find a main effect of aspect ratio and accuracy, similar to experiment 1, such that bar marks with tall aspect ratios were significantly more variable than those with square ratios, but there was no difference between marks with wide and square aspect ratios in either condition. Overall, in the direct replication condition, we replicate the findings of experiment 1 that show that the aspect ratio of a bar mark with area held constant can bias position estimates. For the variable area condition, we again found the same pattern of results, such that the wide aspect ratio marks were consistently overestimated, but tall ratio marks were underestimated, and those with square aspect ratios were not consistently biased. Above and beyond the influence of aspect ratio, area does not appear to bias position estimates. Rather, aspect ratio seems to be the incidental visual property behind this position bias, with the direction of this bias driven towards the categorical prototype of a square. So in conclusion, different aspect ratios of marks appear to elicit varying degrees of bias in position estimates of bars, specifically resulting in a consistent overestimation for bars with wide aspect ratios, no significant bias for square ratios, and consistent underestimation for bars with tall aspect ratios. These findings also appear in line with the effects of a categorical prototype, such that the position recall of these marks are drawn towards the vertical position of a categorical square. So, while we think of bar charts as being encoded by position, length, or maybe even area, it is the incidental encoding channel of aspect ratio that turns out to play a major role in influencing biased recall of data values. The encoding channel that you use may not be the only one that viewers use. And while we tested a few incidental properties of bar charts, we might expect similar incidental encodings and similar biases across other data encoding channels and chart types. Thank you to everyone in the Visual Thinking Lab at Northwestern, especially my co-authors on this project, and thank you all for listening.
So thank you for a very interesting paper on an implicit feature. Some of the questions that have been posed in Discord are already causing answers pointing to the future papers, but I'll still continue these. We have a couple. One is Robert Kosara asked, did you only test perfect squares or so only test squares or rectangles, or did you look at things that are almost squares but wider? And he pointed out that circles can appear more circular when they're slightly compressed. And he's wondering whether you think there were artifacts like this in this study.
Yeah, so it's a great question. So we did test like slightly off squares just because we wanted to introduce some noise into the stimuli so participants didn't memorize the stimuli exactly. So I believe that we had about 3 different conditions and they varied in pixels. I believe about like 25 pixels between like a medium square, which is that perfect square, and then a tall square, we call it, and a short square. But we actually only analyzed the data for that perfect square just because that was the condition that we held constant in area across the 3 different aspect ratio types in experiment 1. So I think that we definitely could look at the data for those kind of off squares, and it would be interesting to see if we find a difference there for sure.
And so with respect to that, this is my question, and the question about categorical prototypes, right? Do you think these are just perceptual primitives, or do you think that these would arise in cases where there are learned shapes or learned visual patterns in a great deal of expert domains? People learn at a very deep level what to look for. So what do you think a prototype is?
Yeah, it's a great question. I think it's definitely the latter, so a little bit more experience driven. I think if you have extreme experience with a certain type of stimuli or a certain shape, then that's definitely going to become the prototype for you. So I could see that varying across different people based on experience.
And finally, there's a question from Danielle about what happens when things aren't axis aligned. Axis alignment is always considered to be one of the, in the perception hierarchy to be very high up. But what happens when these things aren't axis aligned?
That's a great question that I wish I had an answer to. None of the work that we've done in the lab so far has looked at like the misaligned axes. I think that would be really interesting to see if there is an effect of that, and if so, why.
Thank you. Okay. Also, Michael Carell is asking, how much variation is there in aspect ratios and bar charts? There are occasions when people design, they will actually apply a 2D mapping. So width meaning one thing, height meaning another, but realistically, how much variation is there in bar charts overall to indicate where this might be a problem?
Yeah, that's also a great question. I think within bar charts themselves, there isn't a great deal of variability. If you look at like MECO charts, for example, those do have a great deal of variability. Same with tree maps. So you could expand past bar charts. We really just use bar charts as a case study because they are a very frequently used type of visualization. But you could also expand out and look at how other graph types might have an effect of a categorical prototype effect.
Yes, thank you very much. I'd encourage you to look at the Discord channel because there's a lot of interesting questions and discussion happening here. So thank you very much.
Thank you.
Yes, so in keeping with this research, we now move on to the next paper in the series, which is called No Mark is an Island. Precision and category repulsion biases in data reproductions, again, coming out of the same lab. And it's going to be presented by the first author, Caitlyn McColeman, who is currently a senior user experience researcher and formerly a postdoctoral researcher at Northwestern University in the Visual Thinking Lab.
No man is an island, and no single mark conveys data without context. Is this a small value or a large one? Small or large is relative, and a single data point is rarely meaningful without comparing it to at least one other. Adding this larger bar puts the first in context. Now the smaller one is 48% as big as a ratio. These two values can be put together into the context of a single stacked bar, again with the lower value representing a ratio of 48%. The perception of a graph value is impacted by its 0 point, its 100% point, and even an implicit 50% midpoint. For example, we're about to show that values of around 48% are repulsed from the 50% mark such that they are remembered as lower than they are. Let's talk a bit about categorical perception. The following sound will morph from the sound of ba to da in a series of equal steps. See if you can hear each step.
Ba, 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 da, 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 da.
I bet that you didn't notice each step. Instead, the sounds were probably similar until around halfway through the sequence. Then they suddenly changed from the category of ba to the category of da. In an experiment, we could plot the percentage of people who hear da and ba, and it might sound like this.
Ba, 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 da, 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 da.
It's not just phonemes. Other dimensions show the same sort of categorical repulsion. Similar categorical repulsion can be found in faces, varying equal steps in emotion space. A very sad face is more confusable with a kind of sad face than a kind of sad face is compared with a kind of happy face, because faces crossing the happy-sad boundary appear more different than they actually are. We tested whether adding a context bar would cause reproductions of the smaller bar to be biased by the categorical 0, 50, and 100% points. We asked people to draw a bar they had been shown briefly. They'd see a bar like this. We would then take it away and ask them to use their mouse to draw it again at a different part of the screen. Error is how far away the bar they drew was away from the first one that they saw in terms of its height. We tested 3 different types of bar graphs in our experimental conditions. The bar-only condition is a control of sorts. The bar graph presentation has a big bar as a reference on each trial. The stacked has the range of possible values indicated by the surrounding box. In each condition, people saw any value from 1 to 2 to 3, all the way through the possible range of values from 1 to 100%. Participants saw one kind of graph at a time as a block of trials. We'll leave this mark as an example. When participants redrew the presented stimulus using their mouse, we recorded the error. They could recreate the value exactly, or they might overdraw or underdraw exactly what was on the screen. When the bar was redrawn as shorter than the original bar, the participant has underestimated the presented value. We can represent the error as a distance between the correct and the incorrect answer. So we'll represent with a dot the vertical position the participant drew and keep track of how far that redrawn position is from the height of the original bar. When participants draw the bar as taller than it was, they've overestimated it. Again, we represent the distance between the original and the redrawn bar to visualize the error. The over and underestimation is an important source of information for us. We will display how far they over or underestimated the display relative to the correct height, like this. In this case, the bar is underdrawn. In this case, it's overestimated. In this case, the presented value is lower, and the bar was drawn way too high. The overestimation is relatively large. In this case, it was drawn a little too low, and the underestimation is relatively small. We will display how far they over or underestimated the display relative to the correct height, using the distance from the draw dots from the original value. So we can see the assigned error for each of the presented values and have a record of what the height of the original presented value was all in one display. We'll keep track of the drawn value with dots. Here, a participant overestimated a short bar, underestimated a tall bar, and so on. Instead of showing the bar itself, we use an axis to represent 0 to 100% bar height. That way there's more room for the data. This measure is signed error. It shows the directionality of the error. Participants can underestimate or overestimate the height of a bar. Absolute error is our accuracy measure, and signed error is our bias measure. Absolute error is the distance between the drawn value and presented value, irrespective of direction. The same bars that were overestimated in the signed error are shown here to the right of the axis. The underestimated values are simply flipped, so we can see the distance from the correct value. We look at absolute error and signed error for 3 different kinds of bars. In this plot, the y-axis shows the height of the bar, and the x-axis shows the absolute error. These data show the bar-only condition. Notice the absolute error is worse for the alone bars when they are higher. We find the same increasing error pattern in an online replication. Higher bars are associated with higher error. All of the results we talk about today replicated in an online experiment using a totally different code base. We're going to stick with just a subset of the experiments to ensure we have time to cover all the main ideas. Notice that when the presented ratio is closer to 100%, that there's more error than when it's closer to 0%. This may be because error is proportional to the height of the bar. And with the stacked bar graphs, the absolute error is lower overall, especially for those higher values. Interestingly, in the stacked bar graph, we see lower absolute error, but a strong bias pattern is shown in the stacked bar graph when we looked at the sign error. In the stacked bars, values approaching 50% are underestimated. Values exceeding 50% are overestimated. The bar graph condition shows an intermediate pattern, where absolute error is moderate and there's little evidence for the repulsion around 50%. So, it appears in the stacked bar graph condition, participants are repulsed from this 50% value. The signed error pattern suggests that there are starting points for the error and that the stacked bar graph has two reference locations. Performance is near perfect at the start and at the end of the range of the stacked bar graph. Very small and very large values have visual references that in the eye can use the ends of the stack to compare the bar and make better reproductions. In the alone bar condition, there's only one reference. It's just the start of the range of values, or the 0% mark. These data support two major conclusions. 1. Error increases as presented value increases. 2. Responses are repulsed from 50% when there is context added, like in a stacked bar graph. Bars change in multiple ways, though. With an increase of 1% in value, yes, the position of the top of the bar changes, but so does the height and the area. How do we know what the source of the observed error and bias is? We isolate position in a second pair of studies to test whether position is the source of the observed error and bias. Instead of using a bar, we just use a simple dot, either alone, with a reference, or integrated with an axis. We see the same pattern when we isolate the position encoding. 1. We find error increases as presented value increases. 2. Responses are repulsed from 50% when there is context added. In this case, the dot integrated with an axis. Integrating the graph mark with an axis elicits the same perceptual repulsion as a stacked bar graph. Our first two findings then are 1. Error increases as presented value increases, and 2. Responses are repulsed from 50% when there's added context, and that appears to apply to position regardless of whether it's a bar or a dot. We have a third error measure that may help to guide some design decisions. That's proportion corrected error. Recall absolute error is the distance from the correct value and the drawn value regardless of the direction of that error. Signed error is the distance between the drawn value and the correct value, taking into account under and overestimation. The proportion corrected error is the difference between the drawn bar and the correct bar divided by the value of the correct bar. In this case, the original bar, represented by the black, is a bar graph reflecting 65%. The participant redrew it, but remembered it as 60%. They were off by 65 minus 60, or 5%. The proportion corrected error is that 5% divided by the height of the original bar. Proportion corrected error for this example is 0.07, which means that as a proportion of the presented value, the participant was 7% off. In both bar and dot plots, we find that most responses are within 10% of the presented value, just like this example. Proportion corrected error maps to Weber's law, which states that the perceived magnitude of a stimulus, like the height of a bar, is proportional to the actual magnitude of the stimulus. In bar heights, 10% of a short bar is a smaller number than 10% of a large bar. Knowing whether there is a proportional constant for error can help to inform design and communication. If readers are within 10% of the correct value, is that acceptable for the design scenario? If all values are small, perhaps it's better to rescale the data so the perceived magnitude of the values is more in line with the actual values that the bars are representing. In both the bar and the dot plots, we find that most of the responses are within 10% of the presented value. Notice here how most of the data follows a line around 0.1. That's that 10% of the size of the presented value. The proportion corrected Absolute error offers a third finding from these data. Errors are typically within 10% of the magnitude of the drawn bar or dot. An influential paper on graphical perception heralds position as the most precise encoding. We don't argue that position is precise, but we do observe biases in how people remember data encoded using the position channel. What about other visualizations? Are scatter plots subject to categorical biases? What about pie charts? Earlier work has found a cyclical bias pattern in pie charts. In this case, the error around 100% is very low, and there's an observed repulsion from 100%. In contrast to our work with the stacked bars and dots, these folks found 5 reference points in the pie chart, one at 100, one at 75, one at 50, and one each at 25 and 0%. Categorical perception biases people away from these reference points. In our own work, the error pattern suggests categorical perception and 3 reference points, most saliently the one at the 50% mark and the 2 ends of the stacked bar graph, the 0 and 100% marks. We find, overall, that error increases as presented value increases, that responses are repulsed from 50% when there's added context, such as a stacked bar or an axis to reference, and errors are typically within 10% of the magnitude of the plot. Thank you for listening.
We can start. Thank you. So thanks for a really interesting talk. I'm having a very hard time monitoring the Discord channel because the comments are just flying by. So I'm going to pick a couple of questions and again, encourage you to go and spend some time there. So let's start with one that came from Danielle. It reflects an earlier questions, which is, do you think tick marks would help? Some kind of axis labeling. I'm particularly thinking on work that showed that tick marks bias relations in sliders.
I can't speak to sliders directly, but I can pretty confidently say that tick marks would help overall accuracy. So we showed an example of a stacked bar graph that had no additional tick marks, so it's just a 0 and 100. If you look at the proportion corrected error there, it's lower than the other conditions. So having the additional reference points did improve accuracy. So especially building on earlier work from Spence and colleagues, having additional tick marks is going to invoke a little bit of additional bias, but the distance from those extreme points on the bias is going to be closer to the center than if there were fewer tick marks. So if your goal is overall to improve precision, I think tick marks are a really great idea. But I mean, with great power comes great responsibility. If the goal is to overall improve accuracy, that's one way to go. But there are consequences to that decision too. So particular points might have additional bias.
What do you think happens when the meaningful boundaries aren't geometrically even so that the intervals aren't symmetric? Have you considered more, you implicitly have a few boundaries or a few thresholds. What happens if the meaningful boundaries for categorization don't sit in the middle or in quartiles, for example?
I'm moving into speculation here. I think we would see asymmetrical effects. So I'm in my imagination, when I'm trying to answer this question, I'm imagining a logarithmic curve. And so having tick marks that were really close together at the bottom and then separated up further apart as you go up the axis, I suspect that the bias would be, it would be perceptually consistent with the distance between the tick marks in objective space rather than semantic space. But this is speculation, and I think that's a study someone should do. I think that's a good, really great question.
There's another question that says, do you have an hypothesis why there are fewer repulsion points in the bar chart versus the pie chart, and whether this can be generalized?
Yeah, I have a hypothesis. It's due to the number of implicit categories. Circles are perceptually just a different experience than seeing a bar or a line. So I suspect it's kind of to do with the natural categories that arise at the perception of these different shapes. That's a hypothesis. I don't have data for that. But it's pretty clear that circles do exhibit more repulsion points than bars do.
Bernice wants to know, she said, I understand the repulsion at the near equal point at the 50%, but what explains the attraction to the bases?
Start where you start. So I think the attraction to the basis is not attraction as much as it is really good accuracy. So if we have the bar by itself, there's really only kind of one base, and that people are drawing from the bottom and going to the top. So you'll notice that the accuracy at the bottom of that bar is better than the accuracy at the top of the bar, because there's nothing kind of like to say, oh, I'm only this far away from the nearest objective ground truth. I'm using laden language, and I'm sorry, but the base is where the base is, so there's only 1 degree of freedom, in a sense, to redraw the bar. In the stacked bar graph, we have kind of fewer degrees of freedom because we have a 0 set and a 100 set. So you can kind of go to the nearest point to judge what the gap and the distance is. So for folks who are into psychophysics, we might think about it as kind of like two Weber's law starting over again. So Weber's law says that essentially your error is going to be proportional to the magnitude that you see. So high values are going to be associated with higher error. And we have, in a stacked bar graph, we have a Weber's law starting from the bottom up and from the top down. And the bar by itself, we have only just the bottom up. And so I think it's more of a question of where the accuracy is good rather than where is the attention attracted.
So we've had a comment about the strength of the categorical boundary, that the strength of the categorical boundary impacts the degree of reference repulsion. So what happens when considering some of the previous work in this session around semantics, what happens when the strengths of the categorical boundary vary? In a non-abstract test, for example, you could think that the strength of a categorical boundary between happy and sad, which was one of your earlier examples, standard valence question that's really easily set, as opposed to salty and sweet, which has, it may, unless you're particular foodie, may have less compelling nature to it than happy or sad. So how do you think you might measure the strength of a categorical boundary beyond the psychophysical issues that you were looking at? Or do you think that would have an impact?
I kind of want to stay in psychophysical space. I think I might just use a different psychophysical method. So if I want to talk about the strength of a categorical boundary, I think I would want to start looking at just noticeable differences. So the just noticeable differences, if I show you stimulus A and stimulus B, are they the same or different? And then as I get stimulus A and stimulus B to look more and more alike, if you were able to tell them apart, then I can tell you're a really good A-B picker. And so I think that would be a more appropriate way to establish the strength of categorical repulsion. The method of adjustment we used is really slick because it doesn't require quite as many trials. But in terms of determining the strength of category boundary, I think that might be a more appropriate method to use.
Well, thank you very much for a very interesting talk. Lots of people for you to talk to on Discord. So keep looking at that as you go through the conference. And I think we will move to the next talk.
Thanks very much.
Thank you. So our next talk and our final talk in this session will be revealing perceptual proxies with adversarial examples. And this is going to be presented by Brian D. Ondav, and he studied computer science at RPI and bioinformatics at Georgia Tech, and is now a principal engineer at, is now a computer science PhD student at the University of Maryland, and a pre-doctoral fellow with the Genome Informatics group.
Hi, my name is Brian Ondav. I'm a PhD candidate in computer science at the University of Maryland, College Park. Today I'll be sharing our latest research on perceptual proxies in data visualizations. Perceptual proxies are shortcuts that our visual system takes when extracting statistics from charts. For example, when judging the mean in a bar chart, we may simply use the total area covered by the bars. Or when estimating correlation from a scatter plot, rather than performing complex arithmetic, we may really be estimating a visual feature like the distances of the points to an inferred center line. In this work, we'll focus on proxies for extracting the means and ranges of bar charts, using comparative tasks, and drawing inspiration from previously suggested proxies. We'll introduce methods for revealing these proxies using adversarial examples. If you've seen this drawing before, then you know not to trust your eyes when asked which line is longer. These types of illusions may seem like novelties, but they can actually be important windows into how our vision system works. For example, this one works because the angles lead us to infer a three-dimensional scene. Our perception of the length of the upper bar is increased to compensate for its perceived distance. Even when we try to see just the lines, we can't help but use this automatic system as a type of shortcut when making judgments about lengths. We can use this and other illusions as adversarial examples for our vision system. They help expose the shortcuts we take by finding the edge cases where those shortcuts fail. We already know we take shortcuts when extracting information from data visualizations. In fact, this is likely part of what makes them so powerful. But just as certain arrangements of lines can distort their lengths, perhaps there are configurations of bars in a bar chart that can skew our perception of, say, the means of the data series. If we can find and demonstrate such adversarial examples, we could not only learn something about what makes our visual system so good at reading charts, but also help to create visualizations that are more effective and more robust to the cases where that system is not so good. We'll search for adversarial examples using two complementary approaches, theory-driven and data-driven. In the theory-driven approach, we begin with educated guesses for these shortcuts, or perceptual proxies, drawn from geometry, vision science, and existing studies. We'll create charts that are potentially adversarial based on those proxies, and test them with human subjects, providing empirical evidence about our guesses. In the data-driven approach, we won't make any assumptions about which shortcuts are used, and instead we'll attempt to use human subjects to guide the creation of adversarial examples, beginning only from random data. The resulting charts could help tell us something about the proxies we guessed at, or perhaps suggest new proxies that we hadn't thought of. Common to both of these approaches will be a process to maximize the deceptiveness of charts using different optimization techniques for each approach. To provide some common concepts, in both cases the input to the process will be some vector x, which can be thought of as either the raw data or the length of the bars representing those data. For this two-dimensional example, the x-axis is the length of the lower bar, and the y-axis is the length of the upper bar. This maps the space of all possible two-item bar charts. To optimize over this space, we'll need some function f of x, shown by this hypothetical contour plot. For now, we'll loosely define f of x as how adversarial a chart of x is. In the theory-driven case, we'll actually be optimizing pairs of charts. Here, the true statistic we'll ask people to compare is the mean, which is higher in the second chart. We also compute the value of a proxy we want to test, for example, the area of the convex hull, which is like the space filling a rubber band wrapped tightly around the bars. In this case, the proxy, p, is also higher in the second chart. We expect this kind of correlation in random data, since the proxies people use are probably pretty close approximations most of the time. So, to catch the visual system in the act of taking a shortcut, we'll need to create an adversarial example, where the means and the proxy are mismatched in the two charts. If a participant takes this particular shortcut, they would pick chart 1, getting the answer wrong, and giving us empirical evidence for the proxy. To create a pair of charts meeting these requirements, we construct a squared error loss function based on targets for the means and proxies, and use simulated annealing to approximate global or near optima. In the data-driven case, we wish to find out how deceptive a chart is directly from human subjects. In a way, this is the ultimate black box function. We have no idea what this hypothetical function of the human visual system looks like, let alone access to derivatives for gradient descent. We can, however, ask people which of two charts, in their eye, has a larger mean. If both of the charts actually have the same mean, their answer should tell us which one has the larger perceived mean, based on whatever shortcuts they're taking. This type of judgment enables a method called dueling bandit gradient descent, which requires only binary comparisons to optimize a function stochastically. To perform this algorithm, we begin with a random point in our data space, which also corresponds to a particular bar chart. We pick a new point along a random vector, making sure the mean of this new query point is the same as the first point. We show the participants the original chart and the query chart and ask which one has the higher mean, without telling them that the means are really identical. If the participant chooses the new point, we can take a step in the direction to ascend the implied gradient of this hypothetical function of the perceived mean. This gives us a new point with which we can repeat the process until convergence or a number of iterations. To increase the number of those iterations, and to combine input from multiple participants, we perform the process a number of epochs, where the output of one participant becomes the starting point for the next. The proxies we test for theory-driven experiments for the max-mean task are the area of the convex hull, the horizontal position of the centroid of the bars, the length of the longest bar, and the length of the shortest bar. Since there is already evidence that the area of the bars can be a proxy, we randomly choose one chart to have skinnier bars, eliminating this strategy and helping us explore these other proxies. Note that the proxy annotations shown here are not shown in trials. Since our data-driven tasks have no true answer, we don't want participants to begin to wonder or get discouraged, so we mix them among our theory-driven tasks. This way, participants will simply assume they are occasionally getting a very difficult trial among each. Each session comprises 20 trials for each of the 4 theory-driven proxies to be tested, 20 trials for a controlled task in which all 4 proxies have the same ratios as the means or ranges, and 20 trials of human-guided optimization for the data-driven approach, or 120 total trials all shuffled. We run the session for 129 unique participants, 64 for mean and 65 for range. To estimate how deceptive our pairs of charts actually are, we generate trials with a variety of difficulties for each task and proxy. Here are some examples for the max-mean task. In more difficult trials, toward the top, the proxies become more pronounced as they get more mismatched with their means. For example, charts with low means but large convex hull areas, like the orange ones circled here, show goalpost patterns, while charts with large centroids compared to their means, like the one circled here, show piano key-like arrangements as the bars tend toward the extrema. To analyze the results of the theory-driven experiments, we used a hierarchical Bayesian model. First, we used logistic regression to compute tighter thresholds for each combination of individual participant, task, and proxy. These estimate the tighter value, or difficulty, where we would expect 75% accuracy. The higher this tighter value is, the worse performance is. Worse performance, in turn, indicates successful adversarial examples and thus evidence for the given proxy. After computing individual tighter thresholds, we combine them using a Bayesian mixed effects linear regression to compute posterior predictive distributions for each combination of task and proxy. Looking at the individual thresholds for the max-mean task, we can see there is a wide range of performance, with the difference between individuals being greater than the variation among proxies for any given participant. However, there are clear trends that become more apparent if we use the control as the baseline. Tighter thresholds are clearly highest for the centroid proxy, meaning people receive more by adversarial examples constructed using this proxy, and thus that they are likely using the centroid or, potentially, a different proxy that correlates closely with centroid. Moving to the max range task, we see that the picture is not quite as clear. However, aligning to the control threshold shows that the slope range and slope proxies tend to have lower thresholds than the control, meaning they actually help people perform the task better, rather than being adversarial as intended. This could mean participants are using some other proxy or proxy that inversely correlate with these. The patterns we see in the individual thresholds are reflected in the posterior distributions, which model how we would expect new data to behave. They show some evidence for the use of the centroid proxy for the max-mean task, and slope range and slope have weak effects inversely for the max-range task. Since our data-driven experiments are less empirical, we'll interpret the results in a more qualitative way. Here we see our 4 random initializations for the max-mean task, and the optimized results after 5 epochs, corresponding to a series of 5 participants for each of the 4 starting points. These final charts should, in theory at least, appear to participants to have higher means compared to random charts with the same mean, making them adversarial. The first 2, interestingly, exhibit piano key patterns similar to those seen when the centroid is high compared to the mean in the theory-driven tasks. However, while this is largely consistent with the centroid proxy explanation, it's not strong evidence one way or another. Looking at the data-driven max range optimizations, We noticed that they seem to have either notches or spikes compared to the random initializations. This phenomenon doesn't necessarily correspond to any of the proxies we tested, but could suggest new ones. There are several caveats to keep in mind when interpreting our results. We only tested a handful of proxies in the theory-driven experiments, and specifically avoided highly correlated proxies. Thus, evidence for specific proxies, such as the centroid, can be more generally considered evidence for a broader class of proxies. We also don't claim to have an exhaustive list of all possible proxies. On the data-driven, more evidence is needed to show that the charts optimized in this way can actually be adversarial in practice. And of course, in the future, we hope to gather many more than just 4 for each task, which may help patterns emerge. In summary, we use both a theory-driven and a data-driven approach to find adversarial examples that could help reveal how the visual system interprets charts. Max mean task, the strongest evidence we saw in our theory-driven experiments was for the centroid proxy, and this was somewhat supported by the data-driven experiments as well. For the max range task, there seem to be other proxies at play that negatively correlate with 2 of the ones we tested, and data-driven experiments may suggest new proxies. This work has been highly collaborative, and I'd like to thank all my co-authors for their hard work through this tough year, and to thank you for watching.
So thank you very much for a very interesting paper. We're over time, so we only have time for one question. And there are many more and much discussion on Discord, and that channel will remain live. But Danielle asks, super interesting work. What happens when you're working with non-positional data, i.e. data where the arrangement of the values doesn't matter? Can you speculate?
Where the arrangement doesn't matter. That's a good question. So of course the proxies would really change because a lot of them are based on kind of Gestalt type of interpretations of how we're seeing these objects. So I would guess that it would change quite a bit. But given that we don't yet know what proxies are really being used for sure, it's hard to say.
I'd like to thank all of our presenters for really interesting papers and ask everybody please to keep in contact through the Discord channel, which will remain live, and give everybody a hand for a really great session.
Interacting with large datasets could be painfully slow. We can reduce the latency with faster backends, but that's not always attainable. Here, we investigate a solution that only leverages techniques on the front end. We propose interaction snapshots, where users can view the results at a later time. We found that users experienced much less frustration and were able to complete the tasks faster.
Information about vulnerabilities helps defenders prioritize what they need to patch, but this information can be difficult to interpret. In this paper, we support interpretability using a focus and context approach to visualizing vulnerability data, including a clustering overview, plots that enable filtering based on severity, and explanations of text features and descriptions. We invite you to read our paper to learn more.
We have seen many visualizations for tree data structures, but when showing changes in trees over time, some focus on displaying hierarchy, while others highlight their changes. With split streams, we combine 2 approaches and their individual benefits. We evaluated our method in a user study and consider it a general purpose method for the visualization of dynamic hierarchies. Our JavaScript library is openly available.